This is Robert Sapolsky, and you're listening to Father-Offspring Interviews.
Hi there. Welcome back to Father-Offspring Interviews. Starting off, Regspawn from New York says, I'm confused as to why exercise is good for us. Doesn't the cardiovascular system have to work harder during exercise? How is it that regular increase in blood pressure from exercise isn't bad for us? Or is it bad and there are benefits that outweigh it?
One of those great puzzling questions. Okay, two facts we have to start off with. First, exercise is good for you. Second, an insanely large amount of exercise isn't necessarily insanely great for you. You can pass an optimum. So, a concept we've had before, the notion of an inverted U. There's an optimal point of exercise, and too little, and you are slothful, and too much, you got problems there. And in order to get a sense of what's the optimum, where do we get the most benefits, as opposed to what could be the physiological downsides of too much, sit down a hunter-gatherer from the Kalahari Desert and say to them, you know, where I come from, we have so much free time and so much food that sometimes we'll just run 26 miles in a day for the sheer pleasure of it. And they're going to say, are you crazy? That's stressful. By anything resembling hominin history, that's enormously stressful. If you're running 26 miles in a day, somebody is very intent on predating or spearing you and coming behind you. We are not a species that has evolved fast running as one of our advantages. We're not very fast. We're not very strong. We got all these pathetic human primate things, including we don't run really, really fast, and we can't run really fast for a long time. What humans are good at is walking and trotting. And what humans have been successful at forever has been something called persistence hunting. And you see this with Kalahari hunter-gatherers, where the strategy is you show up at one end of the field and there's some kudu who gets a little bit unnerved by you being there as you walk towards them, and they run to the next field and they settle down to eat grass. And then you show up again at a leisurely walk, or maybe even try, and they get up and they run to another field. And you calmly trot after them and do it again and again and again. And what happens is you do this in the hottest part of the day, and we sweat. And if that kudu, instead of walking at the same leisurely pace that you are, is instead running to the next field, it can't dissipate heat as readily because it does it while it's panting, and you can't pant very well if you're a running kudu. What do you wind up seeing? Horrifyingly, at some point, the animal keels over from hyperthermia or keels over sufficiently for you to walk up and spear them. And this is how hunting is done there. By the way, Komodo dragons also do persistence hunting, but they cheat. What they do is they get a bite into the bull, the bison first, and release venom, which over the next few days slowly kills it, as the Komodo, moving at glacial speeds in the tropics there, just keeps following this thing, the stuff of nightmares. Okay, so we've got a sense the optimal human physiology is not built around exercise of running 26 miles in a day. Nonetheless, running is good for you, trotting is good for you, all sorts of aerobic exercise is good for you. So how does a lot of exercise reduces your resting heart rate? Now, the intervening step is with a lot of exercise, your heart muscle thickens, your heart gets bigger. In a way, that's actually good news. Two things go on that cell biology people care about. For one thing, you get hypertrophy. The cardiac muscle cells that are already there get bigger. And that has to do with insulin like growth hormones. The second thing that happens is hyperplasia. You recruit new cells into your heart muscle. You get stem cells that become these things called cardiomyocytes. So your heart muscle cells get bigger. There's more of them. Your heart is bigger there. And what's the consequence of that? It beats with more force. Now, this is very different from another circumstance where your heart gets bigger, where it is terrible news. And this is when you're having so much vascular damage, so much vascular clogging and resistant to blood flow that your heart has to pump harder and harder and harder just to get the same amount of blood through. And it begins to enlarge as a pathological thing, something called cardiomegaly. Not a good thing, which could lead to arrhythmias and palpitations and cardiac arrest. But we're now looking at the good version of it. Lots of exercise, your heart muscle gets thicker and stronger. So, what's a consequence of that? With each pump, it could send more blood more efficiently through your body, so it doesn't have to pump as many times. Your heart rate goes down. And in contrast with cardiomegaly, your heart rate has gone up, and amid your heart muscles getting bigger, and it's all chaotic and terrible for you. What we see with exercise is as the heart muscle gets bigger and thicker and stronger, you pump with more efficiency, so you don't have to pump as often. So, getting back to the basic question, when you're exercising, your heart's beating fast, your blood pressure is up. Isn't that stressful? Isn't that stressful for you? Let's do some calculations here that vaguely approximate the real world. Suppose your resting heart rate is 70 beats a minute, and every day you spend an intensive hour exercising where your heart rate is 130 beats per minute that entire hour. So that's 60 extra beats per minute times 60 minutes. You are increasing your heart rate burden by 3,600 heartbeats. But if you were doing that sufficiently that you begin to get some cardiovascular conditioning so that your heart rate goes down, what you'll see is, say, for that amount of exercising, your resting heart rate drops from 70 to 60, a drop of 10 times 60 minutes times 23, the remaining 23 hours of the day, and you've saved about 4 times as many heartbeats, about 14,000. Get the optimum right there. You can get up to 10 heartbeat savings for every beat of heartbeat exercise and stuff. It's this efficient thing that comes with conditioning. So that's how you could be exercising and get stronger heart muscle and lower heart rate, and it's all wonderful and healthy for you. Turns out there's an extra advantage that comes with this. And this has to do with a physiologist, obscure guy, Joseph Wilder, who in the 1930s, Austrian, German, Jewish refugee, who came up with what is called the law of initial value. Here's how it's stated. You got some physiological system, heart rate, blood pressure, hormone secretion, whatever, and there's your resting levels of heart rate, hormone secretion, whatever, and then your maximal levels that you could produce under the most extreme challenges. And the law of initial value is the lower your resting level, the lower the floor, the higher the ceiling. And it turns out all sorts of physiological systems work this way, including your heart and your blood pressure system. So, what do you see as a consequence? As your resting heart rate gets lower, as you get more conditioned, your maximal heart output, the height of the ceiling gets higher. You are able to accomplish more heart efficiency with maximal exercising. And here's the only decent metaphor I've heard for this. You got a rubber band. You got a rubber band that's sitting at a nice restful state with nobody touching it versus constantly 24/7 chronically basally you're stretching it a little bit. And if you're stretching it a little bit all the time, wear and tear, and physiology is equivalent of wear and tear, so that when the time comes that you want to pull it as much as possible, it's that much more likely to break. If the rubber band is sitting there unstressed by basal demands on its stretchiness, when you try to stretch it maximally, the ceiling is higher. So lower floor, thanks to exercise that's making your heart stronger and beat more efficiently so that your heart rate decreases in a healthy way and your maximal cardiac capacity increases as well. So advantages at both ends.
So now is the question, Why is loss of smell often one of the earliest symptoms of Parkinson's disease, appearing decades before motor symptoms? What is the biological connection?
Loss of smell, anosmia. We've talked previously about the anosmia that lots of people get when they get a COVID infection. How does that work? That's some of the damage that the virus is causing when you've inhaled it and is getting into your brain. If you want to get into somebody's brain, go by way of their nose, not their stomach to their heart or whatever is the deal with men. Anosmia. Parkinson's disease. We talked about Parkinson's a while back, going through its basic features. It's a movement disorder. If you get a choice in the matter, you do not want to get Parkinson's disease. You have trouble initiating movements. You have trouble moving at a normal speed. Your movements are slowed down. Rigidity, it is eventually incapacitating disaster of a disease. And what we covered way back is Parkinson's is centered around a part of the brain called the substantia nigra, which makes very heavy use of a neurotransmitter called dopamine. Now, dopamine is used all over the brain for lots of different reasons. Reward, anticipation. In the substantia nigra, dopamine is playing a role in initiating smooth movement. So, what goes wrong? It turns out, horrible piece of design that when dopamine is broken down just as a normal part of everyday biochemistry, you generate a little bit of an oxygen radical. Not a good thing, but you've got lots of antioxidants all over your brain and body, and that takes care of it. So in most of the brain, you traffic in dopamine, and it's fine that its degradation involves generating a little bit of oxygen radicals. In the substantia nigra, that's a part of the brain that retains lots of iron. And it turns out there's an additional biochemical step so that the kind of wimpy oxygen radical that you generate when you're just breaking down dopamine, then gets turned into an incredibly dangerous one, and it winds up killing neurons there. Okay, so that's Parkinson's disease. So what is the cause of it? Easy version, genetic, a genetic mutation, familial Parkinson's, which is extremely rare, 2%, 5% of the cases or so, where Parkinson's is running in a family generation after generation, about 50% inheritance rate. And what you see there is there's a handful of genes that do not predispose you to Parkinson's, they give you Parkinson's. And you've got one of these mutations, and you're likely to have Parkinson's relatively early in your 50s instead of 60s, and it is likely to incapacitate you much faster. The familial genetic versions of these neurodegenerative diseases get you younger, and they're more severe. So those are the easy ones, except that's only a tiny percentage of the cases. What's going on with the rest? Are there genes causing it? No, we just defined these are cases where genes are not causing Parkinson's. There's all sorts of genes that predispose to Parkinson's that increases your risk for it. What else predisposes and increases your risk? Environment. And amid all sorts of neurological diseases, you could find clinically exquisite descriptions of epilepsy from thousands of years ago. All sorts of these dementias have been around for a long time. Parkinson's has really only roared onto the scene around the time of the Industrial Revolution. And there's lots of reasons to think that pollutants, toxins, neurotoxins that are byproducts of various industrial processes have played a role in causing Parkinson's disease. You see clusters of Parkinson's with people who work with lots of pesticides, pesticide applicators, farm workers, invariably undocumented farm workers with no medical insurance who get sprayed with pesticides with great regularity in the field. Increased risk of Parkinson's. People who work with various industrial solvents, people who do lots of welding, people who do smelting. And what you get is a whole bunch of these compounds that are generated by some of these industrial processes that seem to increase the risk of Parkinson's. And amid that is one pesticide called paraquat and some related compounds. There's a drug that people stumbled into by accident decades ago called MPTP, which is wildly predisposing to Parkinson's. And it structurally is doing some of the same stuff, making your substantia nigra suddenly get blasted away with oxygen radicals. So what we have is officially lots of people could be exposed to these environmental toxins without getting Parkinson's disease. Lots of people have genetics that doesn't predispose them to Parkinson's disease. What we have here is a famed gene environment interaction. People who have a certain genetic vulnerability and wind up in certain environments with a lot of these neurotoxins, those are the ones who wind up getting Parkinson's disease. So we now have a very concrete question, though. You got this stuff coming off of pesticide guns and coming out of smelting factories and all these things. How are these things, these neurotoxic particles, getting to your substantia nigra? And basically, there's three ways that bad stuff in the outside world can get to you. One is by inhaling it, another is by ingesting it, and a third is by absorbing it through the skin. And it looks like with these environmental neurotoxins, inhaling and ingesting are the main routes for it. So inhaling, what you wind up seeing is people who wind up getting Parkinson's 10 years later at a surprisingly high rate. I think something like 25% of cases years before there's already problems with olfaction. There's already anosmia. What does that mean? These neurotoxins have been inhaled, do bad stuff to your nasal machinery there, just like the COVID virus does, causes anosmia, and it now spends the next 6, 7, 10 years slowly working its way in your brain to the substantia nigra, not causing much damage along the way because you don't have this fancy vulnerability that you've got in the substantia nigra. Other route, you ingest it, and 5, 6, 10 years before Parkinson's, another subset of people begin to have gastrointestinal problems of a sort that turns out to be due to these environmental toxins. How do they get from your gut up to your substantia nigra? There's this nerve called the vagal nerve, and what you see is these toxins very slowly meander their way up the vagal nerve, taking over years and years and getting up your brainstem and getting to the substantia nigra and causing problems there as well. And a rare subset of humans have to have this vagal nerve cut, vagotomies, and what you see is decreased vulnerability to Parkinson's disease in there. So you lose the sense of smell because some bad stuff has just gotten in and is starting a 10-year sojourn through your brain to get to the part where it's going to do the most damage, or the gut scenario. And again, does this explain all cases of Parkinson's? I don't know. The most I've seen is 25% of people with Parkinson's turn out to have had anosmia or some gastrointestinal disorders in the years before they got their diagnosis.
I guess you could say we've now talked about anosmia ad nauseum. Ending today, Jenny from Wisconsin asks, is it possible that neural implants of the future could help people strengthen their brains? For example, if a person has an underdeveloped PFC from an adverse childhood, could those implants foster neuroplasticity?
In theory, yes, and maybe sooner than you think in practice, yes. And of course, be careful what you wish for, law of unexpected consequences. So, Flash Gordon aside, there's been all sorts of progress with brain implants, probably most notable company, Neuralink, owned by no other than Elon Musk, that's been developing brain implants. And in the last couple of years, they've been used in, I think, 2 individuals now, quadriplegics, where they gain the ability to control a computer cursor with their eyes. And this is apparently hugely liberating. And this opens up a whole world of people with movement disorders, paralysis, being able to move brain implants to overcome sensory losses like deafness or blindness. But what we have at the end of the rainbow, at least in this question, is being able to use brain implants to change aspects of your self-discipline and gratification postponement and your willpower. Because what we all face is a simple fact: you cannot will yourself to have more willpower. And thus the question here becomes, could you eventually have brain implants in the prefrontal cortex? And we'll touch on that shortly. Can you potentially come up with those somewhere down the line to give people who may not have the willpower, self-regulatory control, impulse control, emotional regulation that is optimal and adaptive, to help them with this? So maybe to get a sense, we should look at what's cutting edge these days, manipulating the brain from outside with high-tech stuff in order to change things like people's philosophies and moral decisions. And this has to do with a technique called TMS, transcranial magnetic stimulation. What you do is you put a magnetic coil just over the place on the surface of the brain that you're interested in, putting it on the skull, on the scalp. And what you're doing there is you are being able to pass an electric pulse through the magnetic coil, and it does something or other with physics. And depending on the frequency of the pulse, you either stimulate or inhibit the neurons immediately below this area. So what that implies is the entire literature is built around manipulating the cortex, which is on the surface of the brain. Techniques aren't there yet to be able to do subcortical areas. So you're restricted to the boring cortex where all sorts of amazing stuff goes on. Now, most of the pioneering work with TMS was simple readouts, movement stuff, because it's a very discrete part of the brain that's involved, and you can collect objective data. Either you hit the button and the person did this with their finger, or they didn't. I actually once visited somebody's lab that was doing stuff like that, and they stuck one of these things on me, and they say, "We're going to make your finger bend right now." And there was no way not to. The weirdest sensation. So they can make people play single notes on the piano that they don't want to, against their will, against their moral compass. More interesting by now are studies looking at how you can use TMS in the prefrontal cortex. Prefrontal cortex that does, as we heard, impulse control, gratification postponement, emotion regulation, does all the stuff that comprises having the willpower to do the right thing when that's not the most appealing thing to do, having the willpower to overcome temptation. So can you use TMS to change people's willpower and moral decision making? Absolutely. One study, nice one that came out of Harvard a few years ago, was looking at moral decision making and was focusing on the prefrontal cortex and another part of the brain called the temporoparietal junction. Temporoparietal junction, that's where you do theory of mind. That's where you think about that somebody knows something that you don't. Their perception of the world might be different from yours. It's perspective taking in other people. Takes years to develop in kids. Totally cool. It's centered in this part of the brain. So they were doing TMS in either prefrontal cortex or the temporal parietal junction, also cortical, and they were giving people moral quandaries. Is it okay for somebody to do this? And broadly, this has been dichotomized in the field, mostly the work of Josh Green, who we've talked about at Harvard, between impersonal moral quandaries and personal ones. Impersonal. A trolley is barreling down the track, is going to kill 5 people. Should you pull a lever to divert the trolley onto a sidetrack that will kill 1 person yet save 5? Can you make that utilitarian trade-off, this being an impersonal setting? Personal setting. Runaway trolleys coming down, and should you sacrifice 1 person to save 5? Should you sacrifice them by pushing them while they're struggling against you onto the tracks? Pulling a nice lever, impersonal, pushing them onto the tracks. Personal one, making a decision about public policy for the budget to help the poor. Impersonal moral decisions, deciding whether or not to lie to protect a friend. Personal moral decisions. And what they saw was by manipulating the TMS in a part of the frontal cortex called the dorsolateral prefrontal cortex, where you get all sorts of very eggheady cognitive decisions about morality. By doing that, by inhibiting that part of the brain, you changed the way people were making moral decisions about personal moral situations. How come? Because you were taking that uptight super ego dorsolateral prefrontal cortex that's all rational and like a Vulcan, and you're taking it out of the picture, and the more emotional stuff dominates then. In contrast, you take out this part of the brain where you were doing perspective taking, modulate that, inhibit that for a number of seconds with your TMS, and people make different sorts of decisions about impersonal moral situations. Okay, so that's very cool. That's changing the moral decisions people would make by just manipulating magnetic waves. What else? Another study, this one came out of MIT. And what you had was people making moral judgments about whether some behavior was okay or not morally. Should this be allowed? Should this person be punished? And what they showed was you take out this temporal parietal junction, that part of the brain where you're doing perspective taking, and people have more trouble telling somebody else's perspective on the world. People have trouble telling the difference between you wanted to harm somebody and you harmed them, and you wanted to harm somebody and it failed. It didn't happen. Most courts will focus on, in both cases, you wanted to harm the person and you simply missed on this one. When people have this part of the brain immobilized seconds later, they view, I intend to hurt this person, but it didn't work out. You don't know they intended to. You don't have their perspective. So you judge successfully harming somebody else and somebody trying to and unsuccessful at it. You see this as morally bad. This is neutral. So that's mighty interesting. Then another study, actually a series of studies coming out from one of the leaders in this field, Ernst Fehr at the University of Zurich. He's an Austrian-Swiss scientist who's done amazing stuff with this. And he shows you use TMS to inhibit the dorsolateral prefrontal cortex. You take out the superego part, and people have more trouble resisting temptation. You do this. This was a paper in Science, and people are in an economic game, and somebody makes you a lousy offer, and you can either say, I don't accept it, in which case you don't get the offer, and they lose also. You punish them for being a jerk, or you say, okay, you take what you can get. And what you see, people develop more sophisticated punitive play. If you punish the person for giving you a lousy offer, they're going to start giving you better offers. You change their behavior, take out this dorsolateral prefrontal cortex, and you lose the willpower to say, no, I'm not going to take your lousy offer. You can't resist the temptation. People don't turn it down. They do more of that. Other ones, people show temptation problems after you take out this part of the brain. You have more trouble with gratification postponement. This is pretty major stuff. This is not learning how to do your finger. This is making moral judgments about other people's actions. This is impulse control. This is resisting temptation. So all of this opens the way for, whoa, so when the technology comes to implant brain chips so you can do stuff like this 24/7 instead of getting your subject and zapping them for 15 seconds and see what happens at that point. When you're getting to being able to do this more chronically, you are tapping into brain circuits will change, neuroplasticity. And this could be a great way, in theory, to overcome early life adversity. Lots of early life adversity beginning in fetal life. fetal alcohol syndrome, low socioeconomic status, food insecurity, abuse, all those sorts of things. For complicated reasons, your prefrontal cortex doesn't develop as much on the average as in other people. And later on, you're not as good at impulse control and gratification postponement. Whoa, could you take people who, because of their lousy early life luck, have wound up having a smaller than average prefrontal cortex? Can you put in brain chips in there that will give them more willpower? And this would be great because you can't will yourself to have more willpower. I would love to have more willpower to be able to work longer hours and be able to binge watch Survivor and not get drowsy after the third one, and to pass a plate of mommy's molasses cookies and take just one instead of three. Who wouldn't want to will themselves to have more willpower thanks to just having a chip in there? So in principle, this could be totally great. And you can get people who could focus more and work harder and need less sleep. And that could be a great thing. And that may not be a great thing, because greater prefrontal cortical function is a value-free change. And just to put that in perspective, let me cite a few people who are famous historically for being workaholics, working 16 hours a day, doing all-nighters over and over, fanatically hardworking. Hitler, Stalin, Mussolini, Kim Il-sung, Franco, all of these were amazing workaholics. So sometimes having more willpower in your frontal cortex will make you work so much harder to come up with a life-saving vaccine. Sometimes it will make you work so much harder at ethnically cleansing a village. So more frontal cortical self-control isn't necessarily a good thing all the time, and it could bite you in the rear.
And that's all for episode 98. I'm Offspring Sapolsky, and thanks for your continued support of science and the beard.